So we're nearly done with min-cost flow. We're going to start our next topic today. But there was one more little interesting nugget that I wanted to convey to you regarding the min-cost flow problem. You remember at the very beginning, I sort of talked about the relationship between min-cost flow and shortest paths, right? That, min-cost flow sort of has this max flow aspect to it, obviously, but it also has this sort of shortest path aspect to it, that the cheapest way to send one unit of flow is to just find the shortest path from source to sink. I'm going to strengthen that relationship today and introduce this idea of complementary slackness. Okay. And this idea comes again from the perspective of these merchants who are buying and selling widgets, and through the action of the free market solve this complicated combinatorial optimization problem. So, last time we worked a lot with these reduced costs. We talked about feasible price functions. Let's think about these from the perspective of the merchants. So, given these reduced costs, what do the merchants do? Where am I going to see shipments of widgets, and where am I not going to see shipments of widgets? Yeah.
See shipments where the buying cost plus the shipping cost is less than the selling cost.
Right. And what does that mean in terms of reduced cost?
Reduced cost is negative?
Right. So what's going on is that if the reduced cost is negative, then they're going to ship widgets. How much are they going to ship?
As much as they can.
As much as they can. So that edge is going to be saturated. Right? On the other hand, if the reduced cost is greater than 0, what happens? Sorry?
Nobody buys?
Nobody buys, or nobody ships. So what does that mean from the edge perspective?
No flow.
No flow, right? Right? Now I've left out one case. What's left? Okay. What happens in that case? Doesn't matter. We don't know. Okay. Could be anything, and it could be anything, and it doesn't matter what it is, right? Nobody's losing money on it. Nobody's gaining money. Nobody's making money on it. It could be anything. Okay. So, given these, so a flow with these characteristics with respect to the reduced costs is said to exhibit complementary slackness. Okay. And what is this complementary slackness? Well, what it's saying is that if one side is slack, the other side is tight. Okay? So if here you have a negative reduced cost, that is you're sort of slack on the difference between the shipping costs and prices, then the edge gets saturated. Or conversely, if you have a positive one, that it's empty. So these are kind of the slack sides, and these are tight bounds. Okay? And conversely, if you have a slack flow, something that is not 0 and not tight, not saturated? Well, that can only happen if the cost is 0. So a slackness on one side corresponds to a tightness or a 0 on the other side. Okay? And what's interesting about this, what's valuable about this, is that if you have complementary slackness, a feasible flow with complementary slackness is in fact optimal. Okay. Why is that? Yes? Sorry, what was that?
Because like any augmenting factor.
Well, so that would be true if we were that would be the sort of right argument if we're talking about max flow, but now we're talking about min cost flow, right? So it's no longer about whether you can find an augmenting path, but what is our sort of optimality criterion for min cost flow? Negative cycles, right? But by introducing feasible prices, we simplified this, right? We got a better a simpler characterization than no negative cycles, which is no. What defines a feasible price, right? What is it about the price function that then gives something that we can easily check in order to know that our flow is optimal? Yeah. No negative reduced cost edges in the residual graph, right? So it's not the original graph that we're thinking about, but in the residual graph there are no negative reduced cost edges. That gives you a feasible price function, which proves optimality. But if you think about it, that's basically what we've said right here, right? So if we have complementary slackness, okay, where are our negative reduced cost edges in the residual graph? Well, if I had a negative reduced cost edge in the residual graph, that would mean that in the original graph I have an edge that's not saturated. Right? That's the definition of having residual capacity, right? Is that you have a not saturated edge. So this is just another way of talking about having a feasible price function. Okay? Yes? Sorry, that's what I meant by a feasible flow. Right? We're demanding a max flow, so that's sort of part of our feasibility criterion. Okay. Now here's something else interesting that we can leverage from this concept. So suppose that I'm given a feasible price function. Okay. For some optimal flow. Okay, so somebody went away, they computed a min cost flow, they found a feasible price function corresponding to that min cost flow, and then they just told us the price function. They didn't tell us the flow. How do we find an optimal, a corresponding optimal flow? And of course, if the answer, we don't want the answer to be use a min cost flow algorithm, right? That would be cheating. So the question is, does the price function by itself make it easier to find a min cost flow? Yeah?
You can just start putting flow on all negative edges of capacity.
Okay. So let's take one. So to talk about those negative edges, first we're going to compute the reduced costs. Right? Okay. So now, as you say, we can consider the negative edges. What should we do if we see a negative reduced cost edge? Yeah?
Saturated.
Saturated. Okay. How about positive edges? So I'm going to delete them. Okay. So now I'm in a slightly strange situation, right? I've put flow on some edges. I've removed some edges. Does this give me a solution to the min-cost flow problem? Why not? Yeah?
Yeah, the flows might be out of balance.
Right. So at this point, balance is violated. I have excesses and deficits. Some vertices have too much flow coming in. Some vertices have too much flow going out because of this flow that I put onto the negative cost edges. How can I fix that? Yes?
So if you have a collection of edges that you don't know what the flow is, and so this would be a max flow problem.
So what are those edges that I don't know what the flow is?
The ones where the cost is 0.
Right. So zero cost edges are unconstrained. Right? And so what are you proposing that I do in order to figure out the flow on those zero cost edges?
Create a max flow problem where you have to route from your excesses to your deficits.
Exactly. So I'm going to use a max flow to route the excesses to the deficits. On just the zero cost edges. Okay. So if I find a max flow that sends the excesses to the deficits on the zero cost edges, well, now I've got balance everywhere, and so I've solved my problem. Right? Great. But wait, do I know I can do this? Maybe there is no way to route the excesses to the deficits on the zero cost edges. I claim that, in fact, there is a way to route the excesses to the deficits on the zero cost edges, but why do I know that this is true? Maybe I'm just an optimist. No takers, huh? Yeah?
Can we send back the edges of the thing?
So that's what we did on a previous algorithm when we were looking at sort of the reductions to various kinds of special min-cost flows. But here we can't do that because we know that we have to leave these saturated edges saturated, and we have to leave these empty edges empty. So we can't use them to send the flow back. We can only use the zero cost edges. So why do we know that that's going to work? Yes, and that.
We know that the price function went with the flow.
Exactly, right? So we know a feasible function, a feasible flow exists. With this price function. So we know there is a solution on the zero cost edges. Okay. So in a really deep sense, this shows that min-cost flow is really just max flow plus shortest paths, right? In a sense, if once you find the right flow, we saw last time that it's just a shortest path computation to find the price function. On the other hand, if you're given the price function, then it's just a max flow computation in order to find the optimum flow. So min-cost flow is really just lump these two things together into a single problem that's the combination of both. Okay? Good. So final words on min-cost flow. Is just what's sort of the status of min-cost flow. So I mentioned this briefly last time, but we have now seen polynomial algorithms. Right? I say polynomial and not strongly polynomial because there is this m squared, because there is this log u dependence. right? And in your homework, you're going to see something with a log C dependence. And actually a worse time bound, but at least it's strongly polynomial in U, even if it has to sacrifice polynomiality in C. Now, Tardosh, in 1985, gave the first strongly polynomial algorithm. It's used a number of interesting deep ideas. One that we'll mention later is what's called minimum mean cycle. So we had this idea of cycle canceling. Find a negative cost cycle and cancel it. Okay, and we just looked for the, if you sort of design your algorithms right, it's sort of natural, it's kind of the analog of max augmenting path. You could imagine looking for the minimum value negative cycle, right? The only problem is that this is NP hard, so you can't do it. However, it turns out that you can find the cycle not of minimum value, but of minimum value per edge on the cycle. So the ratio of cost on the cycle to number of edges on the cycle can be minimized. And so this might not be the truly minimum cycle, but it has, but it is a good cycle to cancel on. And if you use it, you make sort of significant progress in each step towards a solution. It also uses this idea of epsilon optimality. Which is, in my mind, just another way of thinking about scaling. You think about epsilons instead of bits, and you take a phase, just like we take a scaling phase, you take a phase that shifts you from having a solution which is correct to within epsilon to a solution that is correct to within epsilon over 2. What does to within mean? Roughly speaking, we know that in an optimal solution, you want all of the, you want no negative cost edges under reduced costs. Under epsilon optimality, you allow edge costs that are between minus epsilon and 0. You consider the solution OK if the edges are almost positive. Okay? But this just gives you a scaling algorithm. The real sort of key insight is that if you are epsilon optimal plus, and you have some very, very large positive costs, well, as we were talking about over there, you know, in the optimum solution, if you have a positive edge cost, then you're not going to send any flow. Here, we're working with an approximate solution, so we can't say that we have a feasible price function. Nonetheless, what Tardosh proves is that if you're close to having a feasible price function, then if the positive edges are very positive, they have very large value, then they can be ignored or deleted. That is, the value is large enough to give you a signal that you will never send flow on those edges, mainly because, basically because they're not part of any negative cycle. Okay, so they will not be used. The best runtime, combining all of these ideas, is about m squared, similar to the scaling algorithm that we already described. If you're willing to scale, it turns out you can do better. The best scaling algorithm has a runtime of order mn log c times log u. It's called a double scaling algorithm for obvious reasons. You kind of alternately scale on costs and capacities. Okay? And what's crucial, what that gives you is a running time of mn, which is the same sort of running time as we saw is sort of the best we can do for max flow in general. So min cost flow with scaling can be done in roughly max flow time. The special purpose bounds that we saw for max flow the order m to the 3/2 and such, also apply to min cost flow. You can go back and do the analysis and show that you can do min cost flow using these techniques. And so here's an open problem for you. Maybe I'll put it on the homework this week. The sort of Goldberg-Rao generalization to get sort of order m to the 3/2 log u for max flow has not yet been applied. Okay, and the reason is kind of interesting, or is kind of fun. So I think this would be a fun research problem for somebody who's looking for something in this area. The way Goldberg-Rao generalize the sort of unit capacity time bounds to capacitated graphs is that they introduce a cost function on the edges and use that to sort of steer their capacitated graph algorithm. The problem is that if you already have if you've introduced a cost function on the edges and somebody else comes along and wants to give you a different cost function, it's not clear where you can put it. So they don't have space for the cost function for min cost flow. Okay. So that's the end of the story for min cost flow. Are there any kind of wrap-up questions before we move on to our next topic? Yes.
I just have a question about terminology. What's the difference between, so pseudo-polynomial means that it's not quite polynomial, but here you're using
Oh, no, pseudo-polynomial means that it's not, I wouldn't say not quite, I would say very not polynomial, right? Pseudo-polynomial is a runtime like m times u. Okay, which means that it's actually exponential, right? Because you can write numbers using only log of the value bits, this is actually exponential in the input size, right? And so from the complexity theoretic perspective, that is not polynomial at all, right? Whereas here, since you're talking about a log of u, that is polynomial in the input size. Yes?
So are there any lower bounds in these things?
There are no known lower bounds, as far as I know, for max flow, for min cost flow. In fact, I don't even think there are lower bounds for the next thing we're going to be studying, which is even harder than min cost flow. Right? When you're trying to prove lower bounds, you want to work with the hardest problem you can in order to make it as easy as possible to prove your lower bounds. I've got a complexity theorist friend who says that we algorithmicists are just doing lower bounds for his lower bounds. But it would be, so the natural place to start with lower bounds is in the most complicated problem you can that still is solvable. And that's what we're going to be looking at next, actually. I'm not aware of any results for max flow or min cost flow. I mean, I think there's a lot of suspicion that even like shortest paths, there ought to be a lower bound, right? So shortest paths, if you think about it, I mean, that's a very easy problem, but it kind of has sorting hiding inside it. If you look at it. And certainly outputting the vertices in order of their distance from the source, that's a sorting problem, so you're not going to be able to beat n log n. But shortest path doesn't technically have to do that. You could imagine a shortest path algorithm that gives you the shortest paths tree but doesn't tell you which the closest vertex is, right? None of our algorithms work that way because they all use heaps that take things out in order. But there is actually a wild shortest path algorithm due to Thorup that doesn't and achieves linear time under a strange computational model. So there's some hope that we could ultimately prove a lower bound even for shortest paths, but so far we really don't have anything. I, on the other hand, don't care all that much because lower bounds depress me, right? They tell me things that I can't do. I would much rather be optimistic about discovering some better upper bounds. Okay. Yeah, but then how would the next person get tenure, right? I mean, one person would get tenure for proving that lower bound, but then you're kind of out of business. Okay. For our next topic, we're going to continue our climb up the sort of complexity stack, right? We started with shortest path, very easy, max flow a little harder, min cost flow even harder. Now we're going to look at linear programming. Linear programming is one of the most powerful sledgehammers in algorithms. All the problems that we have studied so far in this class are special cases of linear programming. Okay. And so now we are going to study the fully general problem, and we're going to discover that we can solve that in its full generality. So in fact, just from the next week, we're going to have solutions to all the problems that we studied already. So why was I wasting your time with all of that? Well, because we're solving a much more general problem, our algorithms are not going to be as good. They're going to be slower and more complicated. But let's start by just talking about the problem. So if we think about our min-cost flow problem, which we just discussed, right? Let's remember how I sort of described it, right? So I wanted to find some flow values, which I'll write FVW, right? Flow from vertex V to vertex W. And I had these requirements where I said that the sum over W of, say, I'll use the sort of, let's do a min-cost circulation so that I don't have to worry about S and T. So we want the sum over W's of the flows from V to W's minus the flow from W to V, if I'm looking at flow on edges, should be equal to 0 everywhere. And I want to set the flow on V to W to be at most the capacity of the edge from V to W. I'm going to make it positive. And then I'm going to want to minimize the cost of that flow, which is the cost of VW times the flow on VW. Okay, so this is just a nice English-free description of, okay, maybe there's a little English, but a sort of simple description of the min-cost circulation problem. Okay. Now, if we look at it and try to generalize, what we see are a whole bunch of variables that are involved in linear equalities and linear inequalities, and some objective function, which is also a linear function of the variables. Right? So there's a lot of linearity going on, and so for that reason, we are going to be thinking about solving problems like this. Problems where you have a linear objective function, linear constraints, equalities and inequalities, over a set of variables. So asking it, yes?
Is there a requirement that F is a maximum?
So I formulated a min-cost circulation problem. Right, so I said balance everywhere, and so I did that way. I did that so I could write less. Right, if you can do the same if you want to formulate the min-cost max flow problem. You'll just need to write down some more constraints that sort of say I want to have as much flow as possible going from S to T, and I don't have to have balance at S and T, and so forth. All right, so linear programming was introduced actually before a lot of the problems that we were looking at. So people sort of started with the more general problem, and things, the flowering of max flow came 2 decades later or a decade and a half later in the 50s and 60s. Probably the most famous name to start with is Danzig. But von Neumann was also involved in developing the early theories of linear programming. And as is usually the case, it was driven to a great extent by military applications. This was during World War II. They had to figure out how to ship supplies for battalions in various places, how to best use transportation networks to get stuff where it needed to go, how to destroy the Russian railway network, and so forth. Okay, so these people were working on it. This is actually, we're going to have some fun with this problem because if we just want this sort of general form, right? So we're going to have a collection of variables. We're going to have a collection of constraints. which are linear equalities and inequalities over the variables. Okay. And once we have some constraints, we can talk about a setting of the variables. This is, x will now be a vector. And we'll say that that is feasible if it satisfies all the constraints. And we're going to say that we can have an objective function, which is also linear. So I'm just introducing terminology now. Okay. And we are going to look for an optimal x, right? So we're going to say that x is optimal if it is feasible and either maximizes or minimizes the objective function. So sometimes we'll look at a maximization linear program, and other times we'll look at a minimization linear program. Okay. So now we've got a very general problem statement, right? Here are some linear equalities and inequalities. Find me a feasible x that optimizes my objective function. Okay. With a problem this general, it starts out very mysterious, right? Any idea how we can find the answer to this question? Not yet clear. Okay. We can even back up a little bit, right? So the first question you might ask is there always an answer? So if I give you an arbitrary collection of linear equalities and inequalities and a objective function, is there always an optimum solution to that? Well, no. So we might want to restrict ourselves and just talk about a particular linear program being feasible if there exists at least one feasible point. Okay. So is it at least easy to figure out whether a linear program is feasible? To just find any point that satisfies all the constraints? Even that seems challenging, right? We're going to discover how challenging later on. Now, if I tell you that the LP is feasible, is there always an optimum? I see some disagreement. Some heads are going this way and some are going this way. So is there always an optimum? Yeah?
There could be no constraints, and the objective function could just not be bounded.
Right. That's the key word, is bounded, right? So we say that the LP is unbounded if there are arbitrarily good feasible x's. Okay. Yeah. But is that the only thing that could happen?
Could you also have it be bounded but never actually approach?
Ah, so like Cauchy, right? Can we get arbitrarily close to the optimum but never actually get to it? So we have some topology problems to worry about, right? But that will sort of take care of relatively quickly. So I'm just going to state this lemma right away. Every linear program, actually, let me not state it yet, because how could that happen? Like what sort of constraint could you think about that could?
Strict inequality.
Good. So if I have a strict inequality, right? Minimize x such that x is greater than 0. Right? I'm kind of out of luck. However, the inequality constraints in linear programs are always taken to be less than or equal constraints and not strict inequality constraints.
Infinite variables.
You could also have infinitely many variables. This is true. But I mean, it's quite reasonable to talk about infinite dimensional linear programming, right? And a lot of what we're studying still applies. Yeah?
Non-unique.
Good. So certainly there can be multiple optima, right? That's not necessarily a problem. I mean, if they're all equally good, then you'll just be happy to find one of them, right? So now that I've added this condition, I can state this lemma that every linear program either is infeasible or has an optimum, although possibly many, or is unbounded. And I'm not going to write down a proof for this lemma because it's just, you're just checking that we've exhausted all the cases. And if you look through our definitions, we have. Okay? So we can understand this, the goal of the problem now. But now let me ask sort of another question. So let's just look at the LPs where there is an optimum. Okay? And it's not unbounded. Are we sure we can write down the answer? That's a bit of a worry, right? This is a problem over the real numbers, right? Maybe the answer is square root of 2. Okay. That's going to be a problem if we have to output it. It's going to take us a while. Okay. So can we write an answer? I.e., is there a finite output? All right, that's a bit of a worry. Now, maybe it's possible to write down an answer. But even if we can write it down, how are we going to find it? Well, this is sort of along the lines of what I've asked about max flow. Can we check if an answer is correct? Can we do that in polynomial time? Right? In other words, is LP, actually, so this question, can we check it, is it correct? That's asking, is LP contained in NP? Right, which by cancellation is asking if L is contained in N, but or is LP, can we, if there is an answer, can we find it in polynomial time? Okay. If it's infeasible, can we verify that? Can we show it? So hopefully you can see that there's a whole stack of complicated questions to ask way before we get to actually coming up with an algorithm for the problem. There are these much more basic questions that we need to figure out first. Okay. And Danzig actually made a lot of the progress on this, and others at that time. In the 40s, even though they hadn't yet defined P in the 40s, right? They basically showed that LP is in NP. That is, that it is possible to guess/check an answer. There is a finite output, and in fact, a polynomial size output answer for the problem. They also showed that it's in co-NP, which is to say that you can prove that there is no answer. You can prove infeasibility. Also, with the proof takes polynomial space. So that's really nice. It wasn't until the 1980s, actually, that LP was proven to be in P. So I should say, these guys in the 40s, they came up with exponential time algorithms for these problems. But fortunately, these algorithms, which are exponential in theory, turned out to be very fast in practice. And so this was really a revolution. The ability to solve linear programs allowed a whole new approach to all sorts of problems that needed solving in many industries and so forth. And they just happily used these exponential time algorithms for decades.
Well, that's a silly question. Why did you say that LP is an element of P, but it's contained in NP? Is there a difference?
Oh, sorry, my bad. These are, yeah, elements of. Okay. Okay, so we had this big breakthrough in the 80s where we finally proved that linear program could be solved in polynomial time. That first proof involved an algorithm that, of course, was highly theoretical and esoteric, although it has some fascinating aspects to it. In the 90s, there was actual practical work on practical polytime LP algorithms, which in some cases even rival the exponential time algorithms in their practical performance. Okay? So a real triumph for theoreticians that they were finally able to match an exponential time algorithm. Yes?
Who proved that first that the LP was polynomial?
Yes, so this was a guy named Kachin in Russia. And I guess this was important enough that they actually noticed in America also. So there wasn't a duplication of a proof. Actually, maybe this was the 70s. I think I may be off by a decade. What we had in the 80s was the evolution, and this was in America. A guy named Karmakar came up with what was called interior point, which was a new perspective on how to solve. It was a different kind of polynomial time algorithm, which opened up a lot of new ideas. The newspapers got very excited about it. They said that now we were going to be able to solve the traveling salesman problem in polynomial time. But that sort of led to the development of practical polynomial time algorithms in the 90s. And that's where we are today. We've got some great linear programming algorithms out there, and they're very heavily used. So that's a brief history. Let's get into a formal problem formulation. So it turns out to be convenient to write our linear programs in what's called canonical form, which means we write the problem of minimizing C transpose times x, where C is a vector, x is another vector, such that A times x is greater than or equal to B. And so here, C, x, and B are vectors. Okay. And A is a matrix. Okay. And we'll often use m by n as the dimensions of the matrix. Yeah?
Are we allowed to use dimensions?
Not in this class, okay? Because it'll make some of the things that I say much more complicated. Okay? Yeah, so in fact, n is going to be called the number of variables. It's the dimension of x, of the vector x, and is therefore also the number of columns of A. And m is going to be the number of constraints. So I've got here this slightly odd notation where I've said this vector is greater than or equal to this vector. Right? What does that mean? It means coordinate-wise. So what it is asserting is that you've got these rows of A. Each row of A multiplies x and gives you a real number, and there is a corresponding real number in B. And each of those rows from A multiplied by x has to be greater than or equal to the corresponding number in B. So we have these m constraints, which can be written in the form aix greater than or equal to bi, where I is the ith row on the left and the ith coordinate on the right. Okay. So this is the canonical form of a linear program. Okay. We also refer to C as the objective. Okay. Now, if I'm going to call that the canonical form of a linear program, what had better be true? Yeah?
Every linear program can be written in that form.
Absolutely, right? That's the point of a canonical form, is that you can take any weird linear program and transform it so that it looks that way. Okay. So any LP can be transformed to an equivalent canonical form. So let's think about the pieces of that. So suppose over there in the canonical form, you'll notice that I wrote minimize C transpose X. Suppose that instead I have a linear program that asks me to maximize C transpose X. How can I transform that to fit the canonical form? Yeah? Hello.
Minimize the negative.
Right. So I'll just turn this into minimize minus C transpose X. Right? So you notice I've changed the value of the solution. I've negated it, but it's obviously there's a one-to-one correspondence between the solutions of these two LPs. Now suppose more complexity. Suppose that instead of having my nice inequalities written over there, I have something like, you know, AX plus B is less than or equal to CX, I can't use C, QX plus R. Okay, so that doesn't fit the form. What do I do? Yeah?
Things on the same side.
Yeah, just move everything around, right? So here I'll say AX or A minus QX less than or equal to R minus B, and now it fits the form. Only it doesn't, right? I have something else wrong. So what happens if I have a constraint of the form AIX less than or equal to BI? What should I do? Yeah?
Negate it.
Negate it. So I can turn this into minus AIX, whoops, greater than or equal to minus BI. And now it fits the thing. Now, I mean, none of this is very tricky, but this is perhaps the trickiest of the bunch. What if I have a constraint of the form AIX equals BI? That's a perfectly reasonable linear constraint, yes? Yeah?
You add greater or equal to and this.
Great. So I'll turn this into AIX greater or equal BI and also AIX less than or equal to BI. Right? And that reduces it to the previous problem. Okay? So now we know that we can take any linear program and turn it into canonical form, so we can focus all of our attention on solving canonical form linear programs. Except, turns out that the canonical form is nice for some things. It has a very nice geometric picture associated with it. But if you want to do an algebraic solution to linear programming, it's much nicer to work with the standard form. Okay? Don't ask me who decided this one was canonical and this one was standard. That's what they're called. The standard form says I want to minimize C transpose X subject to the constraint that AX equals B, but X is greater than or equal to 0. Okay? So this kind of takes all of the coefficients, all of the constraints, and pushes them into a bunch and turns them into equality constraints. Somehow it gets by just requiring X itself to have non-negative coordinates. Okay? And so this is very useful for certain algorithms because of the way we use, because of the algebra that can be done in this form. And now the claim is that any LP has a standard form equivalent to it. Now, of course, we could prove this the way that we proved the other one, by taking any imaginable linear program and showing how to transform it to standard form. But we have a slightly easier path now, right? So how should we prove that every LP has a standard form?
Canonical.
Transform a canonical form LP into standard form, because we know we can turn anything into canonical form, and if we then turn it into standard form, we've done what we want. So how do we take this AX, the min to the max we already know how to do. So really it's just about the constraints that we're worried about. So how do we take AX greater than or equal, sorry, I miswrote my that should definitely be a min. I think I probably want this to be a max. But it doesn't matter because we don't have any trouble with the algebraic, with the objective function. It's all about the constraints. So we have this AX greater than or equal to B. And we want to instead write AX equal to B. Well, if we just do that, it's going to change the problem a lot. So how can we get from these inequalities to write things in this form? And the answer is we introduce a bunch of new variables, which are called slack variables. Okay. And we'll call these SI, and there's one per constraint. And now, instead of writing AX greater than or equal to B, we write AX, we write AX minus S equals B, or AX equals B plus S, right? And we write S greater than or equal to 0. Okay. So why does that accomplish what we wanted? Or part of what we wanted? Well, you notice we now have the equality constraints, right? We turn things into equality constraints. But what does this S greater than or equal to accomplish? Yes?
It introduces new variables like x greater than 0.
Sorry?
It introduces new variables like x greater than 0.
Right. So it introduces new variables. And the advantage of these new variables is that now if I have an AX which is greater than or equal to B, well, I can just take the difference and call that S, right? And saying that S is greater than or equal to 0 is forcing AX to be greater than or equal to B. It's not possible for AX to be less than or equal to B if I'm going to force the S's to be greater than or equal to 0. So slack variables let me transform from these inequality constraints into equality constraints. But I'm still not done. How come I'm not done? Yeah?
Because you said that all the x's have to be positive.
Right. I need to bring in x. I need to force x. I need to be able to add the requirement that x be greater than or equal to 0. And that requirement was not present in the original canonical form. And so if I just write it down, I'm ruling out some solutions which I shouldn't rule out. So in order to get around that, I'm going to split my variable x. I'm going to write each x as x equal to x positive part minus x negative part. Okay. And then I am going to enforce that x plus be greater than or equal to 0 and x minus be greater than or equal to 0. And I'm basically going to go through, all of my constraints, and everywhere x is written down, I'm going to write x plus minus x minus. Okay, so now any x that wants to be negative, it will set a positive value on x minus and set x plus equal to 0. Any variable that wants to be positive will set a positive value on x plus and nothing on x minus. But each of these parts will therefore be positive. Okay, so these two steps of slack variables and splitting variables allow me to transform the canonical form into the standard form. Okay. So as I already mentioned, the canonical form is generally prettier for theory. And the standard form is what's generally used in implementations. And as we go through, we'll see that. Okay. So now I've defined linear programming for you. For the next couple of lectures, maybe 3, we'll talk about how to solve problems that are presented to us in this way. But to give us some energy for that initial solution, let's take a 2-minute break, and then we'll come back and work on solving. We're going to creep towards the algorithmic solution that we want. We're going to go in steps, building up questions. The first thing we're going to ask is, what does a solution look like? And sort of address the question, can it be written down? Is it easy to verify correctness? And the converse of this. So verifying correctness is one thing. Is there a small proof of having no answer? That is infeasibility. Okay. And only after we've sort of looked at all of this will we ask the question of whether the answer or the non-answer be found efficiently. Okay. Now, we're actually going to do this all in this class, but not for linear programming, but we're going to start with something simpler. Okay. So our sort of toy case that we're going to start with is linear equalities. Which is going to give us insight into how we do all of this, and also give us a bunch of machinery that we're going to need when we solve, when we consider the case with linear inequalities. Okay. So what we're going to ask is, what we're going to look at is solving ax equals b. Okay. So what do we know about solving ax equals to b? Okay. So the sort of case that we learn in high school is when a is square. And there's a unique solution. Right? So if a is square and there is a unique solution, we understand how to solve this. But let's sort of work through things in this process. How do we demonstrate that there is a solution? How do we show that there exists a solution? Yeah? I didn't say how do we find the solution. That's too hard. How do we demonstrate that there is a solution? Yeah?
Plug no numbers in.
That's also an algorithm for finding, right? I don't care how you found the solution. I just want you to be able to prove to somebody else that there is a solution. I love it when these too easy questions throw people off. Yes?
You have more variables than you have constraints?
This is a criterion for when there's a solution. But if I just want to prove to you that there's a solution, how will I do it? Yes? Another criterion. Yes? Is it too hard? Plug what in?
Plug in your solution.
I don't have one. I'm sorry, I have one, but I need to prove to you that I have one. What do I tell you in order to prove that there's a solution? Yes?
Give you the solution.
X, right? Give X. Okay? Oh, that was hard. Okay. And once I give you X, verification is easy. Right? You just do some multiplications and additions and you're done. Okay. Now, if we do want to find it, right, we can find it using, for example, Gaussian elimination. Right? Which I'll assume you all know because I don't remember how to do it. But there's a question in here that's sort of hiding. Can we write down the answer? I mean, I said give X. And you know, our high school teachers are very nice to us, right? When they give us one of these problems, they make sure that we can write down x. Right? But do we know that that's always true? So to answer that question, we have to talk about the sizes of numbers again. We did this a little bit with min-cost flow, right? And we'll come back to that shortly. Yeah. So before we do that, let me write down a few equivalent conditions for solvability that we're going to use. So this is stuff that we all know. For square matrices, having A be invertible, having A transpose be invertible, having determinant of A not equal to 0, having an A with linearly independent rows, or linearly independent columns. These are equivalent. Under any of these criteria, AX equals B has a unique solution for some B. And in fact, if the solution is unique for some B, then it's actually unique for every B because A is invertible and so forth. So these are all these sort of equivalent criteria for knowing when you can solve AX equals B. Okay? They're sort of existential. It's not clear. We still have to get into the computational aspects, but this is all sort of basic high school or college algebra. But now let's talk about number size, because we do want to write down x. Okay. So as we have discussed in min-cost flow, right, an integer p takes log p bits to write down, right? And so we'll call that the size of p. Okay. Now, if we have a rational number, we can talk about the size of p over q. Okay, a rational number written as p over q. Well, obviously, we can write that down by writing down p and writing down q. So that lets us talk about the number of bits we need to use to write down a rational number. Now, what if we have a product? Can we say anything about the size? Right? So if p and q are rational, let me use different numbers so that we don't get confused. If I take two numbers r and s, two rationals, and I multiply them, what can I say about the size in bits of the resulting number? Yeah? It's additive, right? So here we get the size of r plus the size of s. Right? And this is obvious. This is clear for integers because when you multiply integers, the number of bits that you need sums. Right? And so if we do this for the numerator and for the denominator separately, then we're going to sum the numerator bits and sum the denominator bits. We are going to define the size of an n-dimensional vector to be equal to n plus the sum of the number sizes. So you might want to just define the size to be equal to the sum of the number sizes. But if there are a lot of zeros in the matrix, that could get you into some trouble. And similarly, for an m by n matrix, we define that to be n plus the sum of the number sizes. So what? Oh, I'm sorry, m times n. So now let's ask some more. What is the, now that we've got matrices and vectors, what is the size of a matrix product, A times B? Well, that also turns out to be additive. You just sum up the two matrices. and ditto for a matrix vector product. So now that we've defined sizes and understand a little bit about how they operate, we can talk about what we want in our algorithms. So now we have an input, an algebraic input. So there's a bunch of numbers. But we can talk about the size of that input by looking at the number of bits that are used to represent each of the rational numbers. Sorry, I should put an O here, I think. So you want to sort of represent each of the you use bits to represent each of the rational numbers, and this gives you a size for the input. So working in standard theoretician style, we want to talk about algorithms being polynomial in the size of this input. But we're going to have to worry about the bits of the numbers as part of our polynomiality. I'll tell you right now, there are no strongly polynomial algorithms for linear programming, and it's not known if there can be. Okay? So we're going to be working with polynomiality in the number of bits, the way we have been in our scaling algorithms, for example. So with this as sort of a framing, now if we ask if we can write down the answer, again, before we get to computation, how many bits are we going to need to write down the answer to one of these systems of linear equalities? Okay? We're going to have a lot of trouble talking about polynomial algorithms if we need an exponential number of bits to write down the answer. Right? So can we argue that the number of bits of output is polynomial? So for linear systems, is the number of output bits polynomial? That's a pretty important first question. And it turns out the answer is yes. Which is a good thing, because if it weren't, we'd be stuck right away. We'd have to start dealing with approximation algorithms, which would be incredibly messy. So how can we prove that the size of the output to AX equals B, that the size of the solution is polynomial in the input? Well, let's use our basic algebra. We're trying to solve AX equals B. One way to look at that is to find X equals A inverse times B. Right? So if we can argue that A inverse is polynomial size, then we're done. Right? If the inverse matrix has polynomial size in the initial matrix, then we're just multiplying a polynomial size matrix by a polynomial size vector, and so we'll end up with something that's polynomial in size. How can we tell if the inverse matrix is polynomial size? Well, we remember that A inverse is equal to, cofactor stuff divided by the determinant of A. Right? OK. So is the cofactor stuff polynomial size? Yeah, because that's just a bunch of, well, sorry. It's actually the same question, right? We have a bunch of determinants up here. We have a determinant down here. So the real question is the determinant of A polynomial size? If the determinant is polynomial size, then we're in great shape because we have determinants up here, and so everything is polynomial size. How can we decide if the determinant of A is polynomial size? Yes?
This can be computed using polynomial operations, like we do Gaussian elimination and
Yes, so notice that each of those polynomial many operations takes two numbers and may multiply them, so that could double the number of bits. So if we double the number of bits a polynomial number of times, that would be bad. So we actually want to take a different perspective on the determinant. So there's this famous formula for the determinant, right? The theoretician's formula, as opposed to the algorithmicist's formula, is you write it as a sum over all permutations pi of -1 raised to the sign of the permutation times the product of matrix entry I pi of I. Has everybody seen this formula at some point in their lives? It's quite an interesting formula. It actually highlights a really deep connection to bipartite matching, which I talk about at greater length in my randomized algorithms class. But basically it says you take a bunch of products, you go through all these different ways of combining entries from different columns of the matrix, and then you have to worry about the sign of the permutation, how many flips were involved. The details aren't important. What's important is that this quantity, a product of n integers from the matrix, is that polynomial size? Yes, it is, right? It's just n, right? It's n times as many bits as the individual numbers in the matrix, so that's still polynomial size. And so now we add up a whole bunch of polynomial size integers, and we end up with a polynomial size integer. Sorry, we have n factorial polynomial size integers. Right? Now, how big can a sum of n factorial polynomial size integers be? Well, it's going to give us a value which is about n factorial times the max integer. Right? So what is the max product? So how many bits are involved in a number that is n factorial times another number? The number of bits is the log of n factorial times the maximum product. And fortunately, the log of n factorial is only n log n or so. So the total number of bits needed to represent this tremendous sum is it's n log n bits, right? But that's still polynomial. Right? But you see, right away we run into this sort of interesting problem that we started maybe with an input that was a matrix that just had zeros and ones in it. And already, just talking about equalities, our output number could have n log n bits. And this is why a lot of people think that there isn't a strongly polynomial algorithm for linear programming, right? Is that your numbers grow insanely just because of the structure of the problem. Even if you started with small numbers, you may end up working with very big numbers. Yes?
Obviously, that's the worst way.
That's the worst case.
I would like to compute my son because it wouldn't be polynomial to compute.
That's correct. This is only this analysis is only in order to analyze the size of the numbers. Obviously, you would compute it a different way. Okay. All right. Where am I? Oh, yes, history. So now we've kind of examined the square case. We know when we have a square A, what to do. What if A is not square? I'm still thinking about AX equals B. How do we solve a non-square AX equals B question? Well, there's a couple of different things to worry about now, right? We may have a long, skinny A, or we may have a really tall, a wide, short A, or we may have a tall, skinny A. And we kind of need to cover both cases. Okay? But notice that in either case, what we're actually asking is whether the columns of A, thought of as vectors, span B. Right? Is there a linear combination of the columns that produces B? Okay. So if I had a really short, wide A, how would I sort of start off sort of simplifying this problem in order to answer that question? Well, I'd probably start by finding a maximal independent set of A's columns. Right? If I have redundant columns in A, I might as well get rid of them. So I'll just look for independent columns of A, as many as I can. And if A can span B, then it's enough to work with those independent columns of A and see if they can span B. Of course, once I've done that, the number of columns will be less than the number of, will be at most the number of rows, right? So now the number of columns is at most the number of rows. But maybe it's less than the number of rows. What do I do in that case? Right? If the number of columns is now equal to the number of rows, I'm in the square matrix case, I can use my inversion, determinant, so on and so forth. But if I have too few columns, I can't invert the matrix. So what should I do? Yeah?
Exclude rows, keeping it independent.
Yeah, so if I were a mathematician, I could probably figure out how to do that in a way that would make sense and work. But last time I tried to do that, it got me into trouble. So what I'm going to do instead is add some more independent columns. Just make them up, right? Add the things that are not currently part of A to get a square matrix. And then I'll solve the square matrix, because we know how to do that. And I better hope that the new columns get 0 coefficients. Right? If I need to use the new columns in order to span B, well, what does that tell me? Well, it tells me there's no solution that doesn't use the new columns. Right? So once I've made the matrix square, I can use this argument that there's a unique solution. Right? And so I'll find that unique solution. And if it works with the original columns, then I know there is an answer. If it doesn't work with the original columns, then I know that there isn't an answer. Right? So this sort of gives me a computational process for solving AX equals B. And now that we've shown that the integers involved are polynomial size, you can conclude from that, although it takes some work, that solving by Gaussian elimination will do the right thing. It will not produce integers that are too large. And so you can use Gaussian elimination to solve this problem. And we've now covered not only the case of a square matrix A, but a matrix of arbitrary shape. Yeah?
Does the finding like it's maximal linearly instead of adding in vectors of L like solving?
Yes, absolutely. So I mean, I'm sort of moving back and forth between existential type arguments and algorithmic steps, right? So in practice, you wouldn't actually need to add these columns. You would use your Gaussian elimination and you'd get your answer. But I kind of wanted a square matrix so that I could argue about its determinant having a polynomial number of bits, so that I would be able to argue that the Gaussian elimination will work and give me a polynomial size solution. OK, so we've made some progress. Where we're going to pick up next time is we've now shown we have a very easy way to check an answer. And we have a relatively complicated way to construct an answer that should work. But what if there isn't an answer? What if there is no solution to AX equals B? Do I have to run this whole complicated Gaussian elimination algorithm in order to prove that there's no answer? Or can we, the same way as we exhibit X, exhibit something that makes it easy to verify that there is no solution? That's kind of the last question sitting around linear inequalities. And once we've answered that, we'll be primed to start investigating linear inequalities, which is what we'll do on Monday. Okay, wait. Is Monday? Monday is Columbus Day, yes? OK, so we won't do it on Monday, but we will do it on Wednesday.